So in this presentation we're going to look at functions of several variables, although in this case it's specifically two variables. So we're going to the variables are going to be x and y. Okay, a function of two variables is rule f that assigns a unique value f of x and y to each pair x y. So suppose here we have x equal to 1, y equal to 2, and this is our function. F of x and y is x squared plus 4xy minus 2. Here what we have is x squared plus 4x times y minus y. So essentially where we have x, just put in 1, and where we have y, put in 2, and then just evaluate it. So that is 1 squared plus 8, 4 times 1 times 2 minus 2. So therefore that is equal to 7. Sorry, just as a quick remark, this YouTube video, something I should have mentioned before, is best viewed in sort of full screen mode. Okay, now let's move on from that. That's just a sort of rough idea how it looks. This is actually what a graph would look like in practice. F of x and y. It's common to actually use the variable z for two-dimensional functions to sort of functions in 3 dimensions. A function of two variables f of x, y can be represented as a surface in a three-dimensional in 3 dimensions by defining z equals f of x and y to be the height above the point x and y. So essentially you have the y-axis down here, the x-axis over here, and now we have a new axis, the z-axis. So that's how we might look at it in 3-dimensional space. Very useful. Okay, so that's just a sort of how we might sort of look at this in the real world. So the rate of change, this is what we're going to do now, partial differentiation. So this follows on from differentiation, and we're going to use all the rules that we would learn in differentiation, but partial differentiation has a special meaning. Now, just first off, let's read that. The rate of change of z in the x direction at the point xy is the partial derivative of z with respect to x. And this is how we might write that there. Now, just to sort of draw this partial derivative operator here, it's a sort of very round looking d, partial derivative operator, okay, as opposed to something like this, dz over dx, which is just normal differentiation. To determine this partial derivative, we differentiate x or z with respect to x, treating y as a constant. Now, what does that mean? Well, let's say we're dealing with normal differentiation. Just y equals k times x, okay, dy dx, this is just normal differentiation, is equal to k. What is happening here is we are just treating k as a constant, and that would be our answer. It's just left alone the whole way through. So that's it. Just as for example, so suppose k here was 2x, y equals 2x. That means dy dx is equal to 2. You just leave the 2 alone, basically, when you're deriving it with respect to x. Okay, and likewise, the rate of change of z with the y direction at xy is the partial derivative of z with respect to y. And again, it's just dz or dz, or the partial derivative of z with respect to y. I'm going to call it d, but it should partial derivative should its proper name. So again, so you treat x as a constant in this case, okay, rather than y. Let's have a look at a few examples here first off. So find the rate of change of z equals x squared plus 2xy minus 3y squared with respect to x and respect to y. So let's just go down here. I have the answers there, but what I'm going to do is actually just start from scratch here. So z equals x squared plus 5xy minus 3y squared. Okay. Now I'm going to highlight what we're going. I'm going to with respect to x. I am going to just slightly rewrite this. So z, I'm just going to x squared plus 5y times x minus 3y squared. Okay. Now, I'm going to underline everything we're treating as a constant. 5y and minus 3y squared. When we're deriving with respect to x, these are just constants and can be just treated like constants. So, derivative of z with respect to x equals x squared. Let's look at that. That's just 2x. Plus 5yx. Well, here we're just, it's a constant times x. So, that's just 5y. And minus 3y squared. That's just a constant entirely. So, that's just minus 0. Or we can just disregard it altogether. So that's the first partial derivative with respect to x. First partial means that there's other types of derivatives that we'll see later on. So let's do it for dy squared. It's going to go down here. So, or dz over dy, or the partial derivative of z with respect to y properly. Now, let's just write it out again. That is, let's go up here. Let's use this one here. So I am going to go back to this line here, that one there, and highlight everything that can be treated as a constant when we're dealing with y. So x squared that's constant, and there's no y term there. This is so we're actually just going to give that a 0 plus 5xy, that's a constant times y, derivative of that is just the constant, so in this case is 5x, minus 3y squared, that is minus 6y, that's just a normal derivative with respect to y. So what we have here is 5x minus 6y. So those are our two first order partial derivatives, okay? Partial derivative of z with respect to x, partial derivative of z with respect to y. Okay. And yeah, that's good so far. Now let's move on to the next slide here. Here's another example. 2x, I'm getting ahead of myself. X squared sine y plus y squared cos x. Okay. Now what we're going to do here is the first partial derivative and the second partial derivatives. Okay. So this is a bit of a long one. Okay. So actually what I'm going to do here, let's do that. So z equals x squared sine of y plus y squared cos of x. Okay. Now first partial derivative, dz dx, is we are going to treat this. So we're going to treat this as a constant, so we're deriving with respect to x. So we're just going to leave it alone. So this is 2x sine y. Now, the next term, y squared, is something we're just going to leave alone. It's a constant, so it just becomes y squared. Now, cos x, the derivative of that is minus sine x. Okay, that's from the tables. So just rewrite the whole thing out again. 2x sine y minus y squared sine x, minus y squared sine x. Okay. Do I have that? Yeah, that's right. Yep. Similarly, you do something very similar here. I'm just going to go back up here. I'm just going to write out dz dy because I just want to get on to the next thing here. dz dy is done the same way. X squared cos y plus 2y cos x. Okay, so that is the first partial derivatives. Okay, now what we're going to do is the second partial derivative. Let's go back here. Find the first partial derivative and second partial derivatives of this. So that's the answers to the first part there. I've talked about the first one, and I just let the second one be because it's just very similar to the first. Let's go on to the next page here. So starting from this point here, this is the first partial derivative. And what we're going to do is get the derivative of that with respect to x again, okay? So, starting off, these derivative of z with respect to x equals 2x sine y minus y squared sine x. Okay, now exact same as the sort of thing again. This part here, sine y, can be treated as a constant. Likewise, minus y squared can be treated as a constant. So what we're looking at is the derivative of 2x, and that's simply 2. So 2 sine of y. And y squared, we're going to leave that alone, so minus y squared. Derivative of sine x is cos of x. So there we could say that the second partial derivative of z with respect to x is 2 sine y minus y squared cos x. Now, something I'll just draw your attention to is the way we write it. I'm just going to write it over here again. So it's a sort of very peculiar way we write this second order partial derivatives. It's the partial derivative operator, then the square term, then the variable, here it's said, over partial derivative operator, that d, basically, the squiggly d, x, or in the other case, y squared. So just remember to see that the square terms, the two superscripts, are in two different places. Likewise, over here, the same thing happens. The second order partial derivative of z with respect to y, or squiggly d squared over dy, squiggly dy squared, is minus y squared sine y plus 2 cos y. That's just done the same way. It's just a sort of repetition of this here. Okay. Okay, so those are the two main second partial derivatives here. Okay. Sorry, not that one. This is the other second order partial derivative. So let me highlight it. This stuff here and this stuff here are the two second partial derivatives of z with respect to x and with respect to y. There's one more thing we should say, is that that's not the end of the story. So what we have here is the this is just the third. This is a third exercise. Actually, I'm not finished on the second partial derivatives yet, but actually we'll just come to this third example. So find the rate of change of z equals 3x squared plus 5x squared y plus 4y with respect to x and then with respect to y. So this is the first and second order partial derivatives. I'm going to sort of skip by this because it's just a sort of repetition of what I've done already. It's very straightforward differentiation exercise. All we're doing is treating some terms as constant and then just getting derivative of other terms. So we're going to take this as a sort of a article of faith, these two answers here. You can try it out yourself if you want to as a bit of practice, but for the time being we'll just take them as an article of faith, those two answers down there, because I want to keep going from that. What we're going to do, okay, second partial derivative notation, something I mentioned here, that the first order partial derivative of z with respect to x, that's how you write it there, and the second order partial derivative of z with respect to x, that's how you would write it there. Again, just to sort of re-emphasize that point, because we are going to use it again. But this is the important part now. This is the mixed partial derivatives. Okay, so this is when we get a derivative with respect to x, then a derivative with respect to y, or vice versa. Get a derivative of y and then they get the derivative of that with respect to x. So we derive with respect to one of the two variables and then the other. Derive with respect to x, then we derive with respect to y. Just do I'll do a very quick example here. So just to sort of emphasize before I get into something heavy going. So suppose we have z equals 2x squared y cubed. Okay. So let's first off dz dx. So we're treating y cubed as a constant, and 2 is also a constant. So we have 2 times 2x, that's derivative of x squared, times y cubed. Again, what's happening there is we are just treating 2 and y cubed as a constant and just getting derivative of x squared. So the answer would work out to be here 4xy cubed. Now the next thing we're going to do is get the derivative of that with respect to y. So dz squared dx dy is equal to, what we're going to do is treat 4x as a constant and then just derive y cubed. So 4x and derivative of y cubed is 3y squared. So the answer is 12xy squared. Now, I've done it in one particular way. First off, I got the derivative, the partial derivative of z with respect to x. Then I got it with the partial derivative of that with respect to y. And this is my answer down here. If I was to go the opposite, get the partial derivative of y and then get that answer and then get the derivative of that answer with respect to x, I would have still ended up at the same answer here, 12x times y cubed, or y squared, 12x y squared. So that's just a very important thing to remember. So find all of the first, second and mixed partial derivatives of this term here. Z equals x to the 4 plus 3x squared y squared plus 7. Okay, so let's go at this. So z equals x to the 4 plus 3x squared y squared plus 7. dz dx equals derivative of x to the power 4, so that is 4x cubed. Now, 3x squared y squared, that's essentially all we're dealing with there is x squared. So that's plus 3 times 2x times y squared. Okay. So what we could do there is essentially that is x squared. Oops. Ooh, gone down there. Too far. There we go. So that is essentially just. Let's get that. That is just 6. Okay. And 7, that's neither constant in terms of, that's just constant terms. No, it's no x or y terms in it. So it's plus 0 because it's just a constant, so we don't have to put that in. So what we're going to do now is get the second derivative of z with respect to x. dz squared, I shouldn't call it d, but just for the time being, let's call it d. It's the second order partial derivative of z with respect to x. So 4x cubed, essentially we're dealing with the x cubed here, so that's 4 times 3x squared plus 6x y squared, so that's 6 and times 1 times y squared. Let's just simplify that. The 4 times 3 becomes 12, and the 6 times 1, because the derivative of x is just 1, is just 6. Okay. So that's the second order partial derivative of z with respect to x. And you can do the same thing here with y. So here we have up here, there's only one term that would have a 3x squared y squared. That's the only term that has a y component in it. So that's the only term that appears here, because there is no x to the power 4 is a constant, 7 is a constant. So we have 6x squared to the power 6x squared times y. And so those are the first order partial derivatives. The second order partial derivative with respect to y, I'll just write it out here. So it is just starting from here. So it's 6x squared times y. So that is d squared z dy squared. That's just a constant times y, so that's just 6x squared. Simple as that. Now all we have to do is get the partial, or the mixed partial. And here's a little exercise. If you just read your notes there, that this is a little exercise that sort of just demonstrates that no matter which way you go at it, you should get the same answer. So 6x squared is, I'll just take it from here. So the mixed ones is, I'm going to take this as my starting point. The first order partial derivative of z with respect to y, that is equal to 6x squared y. And what I'm going to do is get the derivative, the partial derivative of that with respect to x. Okay, so what we're doing here is 6x squared, so we're going to derive this with respect to x, and that becomes 6x squared. So essentially all we're dealing with is the x squared there, so it's 6 times 2 times x times y, it's 12xy. Okay. If I take it the other way around, dz dx, and get the partial derivative of that with respect to y, I would have got the same answer, 12xy, as you can sort of see there. Okay, that's enough of that. That's partial derivatives. That's a good introduction to partial derivatives. What we're going to do from this, that follows on from this, is a thing called partial differential equations. Okay, and what is required in this is a good knowledge of the second order and mixed, or including the mixed, partial derivatives. So that's an important component of this next topic. Okay.